Thanks for stopping by my poster. I will present monitoring results of near-surface materials at the Garner Valley in Southern California. Here shows event and array information. A presents all the analyzed events from 2005 to 2021 recorded at the Garner Valley downhole array, which is shown as the red triangle here. We will also retrieve precipitation and temperature data from the Idlewild weather station, shown as the red square here. The Garner Valley downhole array has multiple seismic stations and pore pressure transducers at different depths, illustrated in B. There is also a crosshole array experiment with 2 stations and a hammer source at 5-meter depth. There are also 2 other seismic stations directly above at 2-meter depth. The sampling rate is 2000 Hz. Therefore, the data can be used to study near-surface seismic velocities and attenuation at very high frequency. Here shows an example. A is the transverse component waveforms at different depths. We calculate the impulse response function around the S-wave arrivals using the multi-taper spectral method. In B and C, we show the example impulse response functions between different sensors with clear peaks representing waves propagating between the sensors along different paths. Here we calculate the impulse response function from all recorded events between the 6-meter and 22-meter borehole stations. There are 2 dominant peaks. The one at T1 shows the travel time of direct waves from 22-meter to 6-meter, while the other peak at T2 corresponds to travel time of waves from 22-meter to surface, and then reflected downward to the 6-meter. Therefore, the difference between T1 and T2 indicate S-wave two-way travel time in the top 6-meter, and we track its variation for temporal change in the top 6-meter. The relative travel time change, dt over t, is estimated relative to the median value from all the measurements. Here are the results. The black dots shows the measured dt over t, and the red curve shows the 11-point average. Green and blue curves present the precipitation and temperature data. As we can see, the dt over t increase with precipitation. Especially, there is a general decreasing trend of dt over t amplitude during the dry years between 2014 to 2017. This suggests velocity variations induced by water level changes in the top 6-meter. Also, maximum velocity reduction dV over V occurs about 64 days after the peak temperature. This time delay is consistent with the mechanism of thermoelastic strain, implying possible contributions from thermoelastic strain. Here we show results based on crosshole array experiment. There is a 1-day example data showing a downswing and upswing of the hammer source. We can see clear phase delay and attenuation of high-frequency signals at stations 41 and 42. Here we show the attenuation results based on the previous example datasets on the left 2 panels, and the results from all events are presented on the right panel. We assume the geometric spreading factor is inversely proportional to the source-receiver distance and calculate the frequency-dependent Q values based on spectral ratios between the 2 stations, 22 and 42. As we can see, the signal amplitude decreased significantly above 800 Hz. Therefore, the obtained Q values are less than 10 up to 800 Hz, implying significant attenuation at the 5-meter depth. On the left, we present the travel time variations at 5-meter depth, estimated by cross-correlating the crosshole array experiment data. On the right, we compare the results averaged in the top 6-meter and at the 5-meter depth. We can see the average velocity variation in the top 6-meter is 5% larger than that at 5-meter depth, suggesting the velocity variations decrease with depth. Considering the correlation with precipitation and temperature data, we propose the major driven mechanisms are water level change and thermoelastic strain. Future work includes analysis of pore pressure data and modeling of thermoelastic strain. This aims to distinguish the contributions from these 2 possible driven mechanisms. Also, with the high-frequency crosshole array experiment data, it is possible to monitor the variation of Q values at different depths. Please let me know if you have any comments. Thanks.